Alright, this is Computer Graphics Video 3. So this video is on rotations. And this is in 2D and 3D. And so, rotations in 2D. These are typically covered in a standard linear algebra course, so I'm going to do a brief overview of those, considering what we've dealt with in the previous video. So, sort of we know from basic linear algebra say that we can, and if you don't know this, this is a fairly easy thing to show, and even if you don't walk through the steps, it makes sort of a fair bit of sense. We can look at an example. So the point being that we know that rotation of xy by theta radians counterclockwise about the origin, this can be done by the following matrix multiplication. So what you do is you take the matrix cosine theta, negative sine theta, cosine theta. And when you multiply xy, get x cosine theta minus y sine theta, and then x sine theta plus y cosine theta. Now, in translations though, when we were working with points in 2 dimensions, we added an extra 1 so that we could do translations. So considering that points, we'll say, in 2D are going to be represented by vectors like this, we just need to change this matrix a bit. So what we'll do is we'll define r theta, and we'll do a 3 by 3 matrix, but basically all it will do is leave the z component alone. So we'll still have these two entries in the upper left, and then fill it in with zeros and a 1. And then we then do, for example, this matrix we multiply by xy1. And if you do this, you basically get exactly the same thing as on the left. Except we get a 1 right here. So in other words, i.e., to rotate a point xy by theta radians counterclockwise about the origin, all we do is we take that r of theta and multiply it by the point xy1. And that will do the job. So, very simple, but before we go to 3D, let's ask this question. How about rotating around other points? So let's say about points other than the origin. So just to clarify, in this particular case, what we're doing is we're taking a point xy right here, and we're rotating it around the origin by some number of radians to get a new point. So what happens if we want to rotate around a different point? So here's the deal. Let me clear the screen and go through that. So we'll say rotations in 2D about points other than the origin. So the basic idea, let me underline all this as sort of the title here. So the basic idea is very simple. What we do is we shift, we rotate, and we shift back. So basically it's simple. So we shift everything so that the point of rotation, the point we want to rotate around, is at the origin. Right, then we rotate, then shift back. So then visually this is what's happening. Right, if we have a point like, say, right here, we want to rotate around there. Right, what we do is we first shift that to the origin. Second is we rotate. And third, we shift back to where we were. Now, the nice thing is, because these are all done with matrices, this can be done using a simple matrix product, right? So because we have matrices for all of these now, this is great. So let's look at an example. So let's say, suppose we wish to rotate by pi/6 radians counterclockwise about the point 4,7. So we can construct a matrix that does this, right? So the matrix which does this will be the following. So the first one, which is on the right, will be translation by -4, -7. This moves the point of rotation to the origin. Then we rotate, and then we translate back. So what's happening, again in order from right to left, is this puts 4,7 at the origin. This then rotates, then puts it back. Or really puts the origin back at 4,7. So if we calculate this matrix, this is what we get. So the result is, let's write all these down. So this is 1, 0, 4, 0, 1, 7, 0, 0, 1. That's the left-hand matrix. We have cosine of pi/6, negative sine of pi/6, 0, sine of pi/6, cosine of pi/6, 0, 0, 0, 1. Here we have 1, 0, negative 4, 0, 1, negative 7, 0, 0, 1. If we calculate this, this is, I'll give the equals and the approximate. This is √3/2, negative 1/2, 15 halves minus 2√3, 1/2 square root of 3/2, 5 minus 7 √3/2. This is just some calculation, 0, 0, 1, which is approximately 0.866, negative 0.5, 4.036, 0.5, 0.866. So this is a, be careful, there's a 1 down here in the lower left, or lower right. Negative 1.062, 0, 0, 1. So what that means is, if you want to rotate a specific point, so to rotate, say, 5, 2, we do this matrix times 521. We get approximately 7.366, 3.17, and 1. And that's the result. So it's really convenient, right? We get to rotate around any point we want. There's a single matrix that does it, and that matrix is constructed out of matrices that we knew about already. So last thing to look at is, what about rotation in 3D? So even though this video is only at 11 minutes about, I'm going to stop here and put rotations in 3D into a separate video.